Welcome back to CodinGame Spring Challenge 2025. The last one was the Winter Challenge. We could check here, past events. Winter Challenge, yeah. Normally get like 2 of these a year. But, well, I don't know what this is exactly, but from what I've heard, this is an optimization challenge rather than a bot programming challenge, which means it's a bit more independent, it's less about pitting your bots against other people and more about just solving a puzzle as efficiently as you can. So it might not be as popular as the bot tournaments, and I might not even spend as much time on it as I normally do, but we'll try it anyway. Welcome in, DJ. Yeah, I don't think I did any coding since Winter Challenge. Wait, was that before or after? Oh, it was coincidental with Advent of Code, but Advent of the Code finished on the 25th, so there was enough time to do it. Speaking of which, I have one Advent of Code left, one archived Advent of Code left to do. I'll probably do that in the middle of this year. So let's have a look at this then. So I managed to make Satisfactory run worse on my computer than it ran yours. I have my entire factory in one location. Oh, right. Yeah, I guess spreading things out sort of helps with that. But you're talking about... Because I did a couple of streams where the performance was dreadful, but it turned out that was because I had OBS Preview on, which actually saps a huge amount of CPU. I don't know, were you talking about that particular stream, or just... Because most of my streams after that were actually not too bad. Also, when I reduced the resolution, turned off the enemy hostility and stuff like that, it seemed actually pretty good. But OBS Preview was the biggest culprit. Hellscape of belts everywhere, yeah. The interesting thing is I read that trains actually make it a bit worse, surprisingly. You would think there would be better than belts, but apparently the whole physics of the trains causes a lot more lag. Yeah, when you were having like 20 FPS, yeah, that was because of OBS Preview. I didn't even realize it at the time. Yeah, I gotta remember. Normally I always turn OBS Preview off once I've confirmed the stream is working, but I forgot that time. I don't know why it sapped so much CPU. I wouldn't think it would, but it does. I guess because it's trying to do it, like, very real time. Alright. Like, it's not as bad, but the performance loss was probably worse. Would drop from 140 plus to, like, 40 when I enter the factory, yeah. Like, people suggested that I should box up my factories. There are pros and cons to doing that. The pros are, you know, when you're outside the box looking in, you're not rendering as much moving objects, so that does help with the CPU. But when you're away from your factory, you're not looking at the factory anyway, so you're just actually using more CPU to keep all those walls and roofs and everything in memory. So it actually is worse depending on how you're laying out your factory. So I don't really agree with boxing up your factories. It only helps in certain cases, but it really depends on how you're laying everything out. Alright. Anyway. The goal
Compute all possible future states of an ongoing game of Mark Steer's cephalopods in the shortest time possible. Oh, we don't. Do we not get a fun game animation window? Apparently not. Okay. Okay, this might not be nearly as exciting as the the usual challenges. I guess we'll try it anyway. I might not devote too many days to this though. Like, I do like the animated ones a lot more. Well, let's try it. Oh, okay. Rules. Cephalopods is an abstract two-player game played with dice on a grid. Have you seen the new 1.1 update for Satisfactory? I only heard about it the other day, but... Well, I think it only dropped the other day, but sounds interesting. Apparently they've actually added a lot of stuff. Optimization isn't exciting, just incredibly necessary. Well, I think a couple of the optimization challenges they've had in the past did have an animation, so they still made it a bit flashy. This one seems it's not quite that. The objective is to find all the possible board states after a given number of turns by simulating all possible moves from a given board state. This version of Cephalopods is played on a 3x3 board, quite a small board, on which players take turns adding dice of their own color, 1 die per turn. Seen in notes, vertical splitters would have made my factory so much less of a mess, yeah. You've got vertical splitters, you've got straight pipes. Something with trains. You can make trains, you can make paths, train tracks that can split up. That's a big deal. Like, that really changes how you lay out your train networks. In fact, that was one of the things holding me back from using trains in my playthrough. The idea that I would have to have a separate line for every transport line. A newly placed die must show a 1, unless it's a capturing placement. More information below. Once the board is full, the game ends, and the winner is the player with the most dice showing a 6. In this exercise, you will not be required to compute the winner of the game. Nor will you need to track whose dice is whose. Okay. If a die is placed adjacent to 2 or more dice, and any combination of these adjacent dice has a sum of displayed values less than or equal to 6, then the player must remove that combination from the board. Alright. Examples will probably help. Played die must then display the sum of the values of the removed dice. But if there's multiple combinations, I guess you choose which one? Oh, yeah, that's the very next line. If multiple combinations are possible, the player chooses which one to apply. Captures are mandatory when placing a die where a capture is possible. If die is placed on a space where no captures are possible, its value will be 1. Alright, I see. Alright, so you place a... So black is the newly placed thing. So place a 1 here, and then capture goes here. You capture the 2 1s and you get a 2. And then here... Oh, this is a different...
board. So oh, there's still a concept of ownership. It's just we don't need to keep track of it. They'll keep track of it for us. So black and white do have their own dice. So white is the one that captured here. I see. Yeah. Okay, I get it. So here, black is to go. Alright, so he chooses to capture all 4 of them. So any combination can be any subset of the up to 4 neighbors. Interesting. So if black is going there, you can go for the 2, or you can go for 5, or we can even go for 6. It's gone for 2, right? Why wouldn't you go for 6? Well, I don't even know how scoring works yet, so... And here... there's no possible capture. If there was a possible capture, you have to take it. Because there's no possible capture, he places the 1. Okay. Hello, cat peasant. Doing some dice game coding today. Read from this. Okay, so far the state space seems quite easy to code up. 3x3 board. And each die has values 1 to 6 and is owned by either player. Guessing points are based on number of dice controlled. So capturing your own would be a dumb idea. Oh yeah. Wait, which example was I looking at? Yeah, this one. Yeah. Black was... oh yeah, that was black's own die. Yeah, so he does end up with more overall. 5, 6. If you went for... oh, it was 6 versus 6, but... or it depends on whether it's number of spots or number of dice, I guess. We'll find out. If it was number of spots, I'd rather have the 6, because that's harder to capture. Impossible to capture, even. Each board state is represented as 32-bit integer using a simple algorithm. Here's how the hashing works. The board is treated as a grid where each square is encoded with a single piece of information, the value of the die on that square. Okay. Left to right, top to bottom. So basically you got the 9 values. And then, okay, so you... okay, each digit of the integer is those 9 values. So to start with, you build up the 9 values in one 9-digit number. We're talking decimal, not binary. And then, right. And then, what if it starts with 0? Well, we haven't finished yet. And then, oh, if it starts with 0, it's fine. It'll just be a smaller number. Okay. Calculate the hash of the final board state at the end of the given number of turns for each game. So if we're... sum all the hashes of all the final possible board states. So it actually, so the motivation of where they place stuff doesn't matter, and that's why we don't need to keep track of black and white, because you could equally capture it whether it's black or white. So we actually don't need to do anything with the player color at all, I suppose. And okay, so we do that. And they'll take a sort of average of your best times. Ah, so that this is not how they normally do it. They're actually timing how long it takes for you to calculate. Ooh. That's a bit worrying because, I mean, it massively depends on the language you choose. And I want to stick with Python, but I'm clearly going to be at a disadvantage. Okay, so yeah, they're taking basically your inner range of times, the eight middle times, 6 middle times, and then average them. Okay, fine. How fast to... Do we have to get it correct, though? We probably have to get it 100% correct. Maybe the boards are separated by language here. That's not usually the case because they support a lot of languages, but we can check. No, it's not. I mean, you can filter it if you want to, but yeah, so the best Python user is at position 261. And the top of the leaderboard is all C++ and Rust. That's, yeah. I guess nothing I can do about that. That's unfortunate. And it also means I probably won't spend much time on this challenge, but we'll have a go at it anyway and do the best I can in Python. Like in the usual AI challenges, Python is like happily a very competitive language to use for them. It doesn't matter too much about the run speed as long as you can get what you want to do done within the time. Fine. So you get Python people at the top of the leaderboard, but yeah, this one is really heavy on the computation. In fact, I might just do this one stream and leave it at that. Alright, we'll try it. Let me just copy in some code that I usually keep. Wait. From the winter challenge. I just want the logging statement. Where's my code? Yeah. Alright, so I'm not going to try and do any fancy stuff with the bit arithmetic, which often is a very, very efficient way of storing like values and stuff. I'll just store things the way I normally would in Python, and we'll see how fast it is. Alright, let's just see what we've got. So in general, we'll be given a one board state, and so we want this concept of state. So let's define is the hang on, they've changed the there used to be a maximize button for this so that you can focus only on the code. Can't even minimize that. Can't even maximize the codes bit. Hope that's not. Oh, hang on. Why am I cut off here? Let me refresh this. I don't know what's happened. Why is this cut off on the side? Did you zoom the page? Oh, because I was hovering the mouse when I zoomed. Ah, yeah, that's it. If you put your mouse over different sections, you zoom depending on where you are. Ah, okay, yeah, got it. Yeah. Zoom in like that. That's what I wanted. Alright, so let's define a state. It's going to be a class. And it's a series of digits, isn't it? It's 9 digits. So if you find let's say D1, D2, D3, D4, D5. Well, okay, we'll use data class here. The data class will work here. Just from data class. Probably want that to be frozen as well. We're not modifying it in any way. All right, define. We don't need to define that then. So basically we have 9 digits. D1 is an int, D2 is an int, or should I call them like maybe I should name them after their row and column. That's probably the easiest way to think of this. So like row 0, column 0, row 0, column 1. Just like that, basically. Two, 1. That. I mean, either I do that, or we actually store them in a grid. But it's kind of more memory efficient to do it like this, I suppose. The advantage of the grid is it's easier to generalize the capturing because it's just based on the grid rather than... actually, that's probably a good argument for using a grid, to be honest. Yeah, I mean, the grid's not that inefficient. It's fine if we do it as a tuple of tuples. All right, let's rearrange this. So So the idea is you take 9 digits and we put them into a 3x3 grid. That makes it easier for us to think about adjacency, neighbors, things like that. So we'll have... At this point, we'll just call them D0, D1, D2, D3, D4, D5, D6, D7, D8. And then I need to look up something that I did before. We need to use this line here. It's kind of like the cheat. So I've frozen equals true means you're not allowed to modify this state. It's a fixed state. That means it's hashable. Important here. And you're never allowed to modify it. The problem is it means you can't even really initialize it in the first place because that counts as modifying. But you can kind of get around that using this line. So we want... I don't know if this is good practice. It might be bad practice. I'm not really sure. I never really used data class in like a proper software engineering environment. So, but it works. So define... No. We want board. And that's going to be basically a tuple of int. Have I even used the right brackets here? I don't... No, it's tuple of int like that. No? So am I allowed to do that first? No. List. I'm allowed to do list. Oh, it is square brackets. Yeah. And then... Okay. So it would be like... we want to set... board the... So basically be D0, D1, D2, D3, D4, D5, D6, D7, D8. Just going to ask why it says D5 is an invalid entry, but it's duplicated. Ah, yeah. D5, D6, D7, D8. That should be it. So the great thing about data classes now, we get a lot of methods for free. We can print it, we can hash it, we can test equality, and it'll do it in the natural way. Try that now, actually. So int I in range 3 for j in input.split value equals int j. Okay, let's just put these into a list. So we accumulate the 9 digits into this list here. And the initial state is going to be capital S. And we should just be able to do star digits. And it should feed the 9 digits in to those 9 parameters. And now let's try logging init state and see what we get. Nice. Okay, so that's not the most mathematically efficient way of storing the state, but it is the most... It is how you would store it if you're going to do anything with that board for practical purposes. Alright, so let's stick with that. So the idea is, given a state like this, regardless of whose turn it is next, and regardless of who owns what die on the board, that doesn't matter. The next player can place the logic of this is quite simple. So when it comes to actually optimizing, it's just probably a lot of tedious stripping away of stuff using like more bit arithmetic and stuff like that. We'll just do it the natural logic way. So let's say all we need is this one method, which is going to be a get next states. Okay, so given our state, we want to spit out all possible next states. And I'm not going to try and do any shortcuts yet, but there's probably a couple of ways we can sort of avoid recomputing loops. For now, we'll just go through all 9 spaces on the grid, and if there's zeros, that is a possible placement. Before I do this, we want our most helpful method ever, which is get neighbors of a given row and column. So in this case, the easiest way is just say for dx dy in, so we got -1 0 +1 0 0 -1 0 1. So that's the 4 possible neighbors. See, stuff like this is just going to keep recomputing through this loop every time we're finding neighbors, when in reality you could actually just hardcode the exact list of neighbors for each cell in your list. We can try doing that and see how it improves things. So for now, we'll just do it like this. New row, new col equals row plus... Alright, let's switch to using i's and j's, because I'm not really thinking in Cartesian coordinates here. New row, new col equals row plus di
call plus dj. If 0 is less than or equal to new row is less than 3 and 0 is less than or equal to new. Yeah, this is actually using a bit of computation here that can be skipped. Yield. Just checking if this... I was having some trouble at the very first couple of minutes of the stream. Seems to be okay now. Alright, yield. New row. New call. That gets us the neighbors. And then get next states, basically we go for like I in range 3 or j in range 3 if self.board I j equals 0. That means someone can place a die there. So we basically have to check all neighbors. Alright, so the best way to do this really is want a little boolean here, keeping track of whether we've been forced to capture or not. If we ever find a combination that forces us to capture, then we're no longer allowed 1 as a value of this die. So we do forced capture equals false to begin with. And if it's still false by the end of this loop, then we know we can place a 1. Alright, so we do for say neighbor dice is a list, let's say. We're going to keep first just accumulate all the neighboring dice. So for neighbor, it's going to be like neighbor I, neighbor j in dot get neighbors of I j. So that's up to 4 adjacent neighbors. If self.board this is another thing we could use a method for, but I can't be bothered. Is 0. No, is just do that. That means it's not equal to 0.
then neighbor dice dot append the value, because we only care about the value. No, we don't only care about the value. If we capture, we have to remove the specific one that we're capturing. Okay, so we do need to store the position. So it'd be like this. Neighbor I, neighbor J. Or we could make it like store the value as well, so that we don't have to recall it later on. Okay, so at this point, neighbor dice has possibly some number of neighbor dice. We've stored both the value on that die and the vector of where it was, because we'll need that when we're capturing. So now we go through all pairs. Now this is the bit where we're probably going to spend way more computation than we need, because if I just do the straight up quadratic for P1 in this list, for P2 in the remaining bit, then that's uses up to like 16 steps, but whatever, we'll just do that. So for P1, what's the cleanest way of doing this? Let me have a think. Okay, for, let's say, x in range dice starting from index x plus 1. So that gets all pairs, but it doesn't avoids duplicating any. We have to now look at the values. So total equals the score value of that plus score value of that. If total is, so it was, if it's at most 6, so then we found one possible neighbor state, and that is what's the cleanest way of doing this? So basically we would need to change those two things to be 0. And everything else stays the same. Oh, and IJ changes to total. So basically we just need to make a clean copy of so we're going to need a method here to get the numbers back as a list. So it'll just be like this. Because we need that for hashing anyway. So get digit list. And that is just like alright, we'll just do it like this. Do it like this. Out of range. Should be okay because it doesn't know yet what we put inside that board, so it doesn't like this indexing. I think it should be okay. We'll find out. So that gets digits back as a list, as a get digits. Or even as a list, I suppose, will actually be more useful here. So here, digits equals of dot get digits. All right, so get the current digits as the list. But we change ij will be total, so it's going to be b times I plus j equals total. Then we want digits. Oh wait, this is pairs, not combinations. Hang on. We need to backtrack here. So we can't do pairs. What we need is to use iter tools to find subsets. Which actually probably will end up being cleaner than this, because it's like a built-in library. Alright, I'll be right back. Oh. Stream has gone down. Alright, the stream went down. Huh. Oh, it's going down again. It's a bit temperamental right now at my end. Alright, well... I will be right back. I'm back up, but it's not. It's not stable. Alright, I've turned down the bitrate a bit, but we'll see. This won't be a particularly long stream anyway. I don't really feel like heavily optimizing this. We'll try and get a solution. Alright, so this needs to be redone because I just remembered we're looking for pairs. No, sorry, we're not looking for pairs. We're looking for subsets. So it could be pairs, it could be triplets, it could be all four. So we need to use like ITA tools or something to do that more cleanly, which should end up making this look better actually, because then we're just kind of offloading the logic to ITA tools. How do we do that? So we've got as far as, so basically from here we need to change the way we're doing this for loop basically. So it's gonna be it's gonna be, let's have a look, ITA tools, like what's the name of this subset? Cartesian product, power set? No, it's like subsets, isn't it? Cycle accumulator product. No, not product. Yeah, it's like product, but not. What's the one that gives you all possible subsets? No, not combinations. Wait, where's the list of things? Could have sworn. I mean, we can just do product, but range over all. Here. We're doing that basically. I thought there was a method which does that. I guess it's just a very inefficient method, but we're only doing it with 4 items, so I guess it's fine. Power set of iterable. That's basically what we want, yeah. So shortest to longest. So we want to modify this. We just want from 2 to longest, so it's going to be like 2. So all non-trivial subsets. Well, that's not the correct term. All subsets of size at least 2. And this is from ITA tools. Excuse me. All right, so here it would have been easier if I used a vector, but that would have consumed more memory. Okay, so we want 4 subset in our set Okay, so take that out. That actually looks cleaner now. Subset and power set. So we know these will be size 2 or more. Total will be the sum of P0 for P in subset. So because the subsets, each item of the subset is a pair. So that's the total. And if the total is less than or equal to 6, then we found one capture. So we immediately note that this is now a forced capture. So no more. A capture has to be chosen. Right. And then we have to say, if we do this, we do that, and then for P in subset, so for each of these things we want to remove the die. So we've got the vector here, so we want to say index equals 3 times P1 0 plus P1 1. So just say digits equals 0. And then we found the neighbor. Yield state with those digits, right? And then that looks fine. And then after we've done that, we then go and say if we never found any capture, if not forced capture, then this will change to 1. So it's going to be like put that equal to 1 and yield that. So I think that's how we get next states. So we can test this out. We can say log initial state, log initial state dot get next states. Let's see what this looks like. We found 2 states because there were 2 empty spaces, no captures. Let's see if we get some captures. So That's the initial state. We can place one here, 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 and here. But we've not tried... Okay, there's no captures there. So, example with a capture. 1, 2, 3. We haven't done any captures. Okay, no, that might not be correct then. Oh no, but these are big numbers, so there's no possible capture. They're giving us ones with no captures. Okay, this one should be a capture. Alright, yeah. So there's one possible placement, but none of these have 1 in the middle because we have to choose one of the captures. So for example, this one, we've taken that one and that one. Yeah, it looks good. Looks like it's working. Alright, we'll assume it's working for now. So we can get next states from one single state. What's next? So we now... Oh boy. So we have a list of state at any point we have a list of states, like a set, and we find the neighbor states of all of those, each one by one, put it all into one big set, and that's the new set of states, right? That's what we do. But the question is, are we expecting to get a lot of repeat states? Yes, probably. There are different paths of placement, which would lead to the same state, but I'm just thinking, do we cache this get states function? Probably. But can we actually cache? We're gonna have to make it an outer method, not sub method of state. Well, we can keep this here. That's fine. But what we want to do is get next states or given state. And this is just like an outer method which is calling this. So we're saying it's just this, right? Return tuple of state dot get next states. But why do we do this? Because now we should be able to just cache this. No, it's not called cache, it's called LRU something or other. How do you do this again? And it's from that. So now we can call this. I don't know if we could actually put this on this. Can we do that? We can, but I don't really know what it does exactly. I'll leave that off. It's alright. I mean, this is not costing us much more. So we can do that. Alright, how do we put this all together then? So we need... we've got a depth. So what exactly do they mean by the depth? So it's like if depth is... So in the first example... What is the depth? Log depth. Is it 1? 20. Oh, there's one important... Oh no, that's already covered. So, if there's no zeros, then it's finished. The game's finished. But that's already efficient because it's checking anyway if there's any zeros. So... We could... Interesting. So if there's a final state, obviously we still count it in our count, but there's no point keeping it in the list because we're just going to keep trying to evaluate its next states every time. So we should actually have 2 lists. One for final states, one for non-final states, and it's the non-final states that will keep evaluating. So let's try that. So we've got all of this stuff. Let me read the wording of what to do with depth again. Depth is the number of times we do a turn, right? Given the number of turns, yeah, I assume. Okay. Let's take this out. Right, so we can log... Yeah, we can log that, that's fine. So we've got basically 2 sets. Set 1 is... So we need one more method here. We need find is final state. If any, if 0 in self.get digits or return 0 not in self.digits, yeah. So we have 2 lists. We have non-final states equals an empty set, and final states equals an empty set. At the very start, they may have given us a final state, so we just need to double check whether it's a final state or not. If if initial state dot is final state, then it goes into final states. That's the setup. Now we're ready to do the process. So for I don't know, D in, or well, it doesn't even matter, for in range depth. We do this depth many times. If, let's say, if non-final states is empty, if not non-final states, then we should just break out of this, really. Alright, otherwise, new states equals a new empty set. And now we go through each of the states one by one. So for state in non-final states, we then find its next states. So for next state in, so we call this method get next states of state. And then we just do this logic again. We choose where to put it. Stop. Right. Okay. If, so it's going to be if next state is final state dot add next state. Otherwise, this one is going to be new states. Right. We want to avoid garbage collection as well, so okay, we'll worry about that later. It's going to automatically clean up some methods if some stuff if we don't use it. And then we just replace non-final states with this new set of states. Yeah. The point is we're kind of siphoning out all the final states so that we don't try to evaluate them again. But the non-final states are the ones which we can take to a next level of depth. And after we've done this, it should just be length of non-final states plus length of final states. Alright, we could run this and see what happens. Then, nope, it's wrong. Response was 1. Correct answer is okay. Correct answer is that. Also, that's huge. I think we are probably overlooking something, and it probably should be taking into account all the rotations and stuff, because there's going to be a huge number. Yeah, that's too big, isn't it? This is, you can't actually simulate them all. You have to well, okay, so why do I end up with 1? That's wrong. Alright, so we just have to log what's happening. Let's see what it looks like at each step. So we start off with that, then we move to we need to put some words here. Should be 2 states. Wait, why is that number so big? What are we actually supposed to be... Oh! I forgot to do the... That's not the number of states, that's the hashing process. That's the final step. Once you've found all the states, you then have to hash them all. Okay, so... Let's do that. But do we have... We don't end up with 2 states. So in the intermediate, we've placed 1 there and we've placed 1 there. That's correct. I mean, that looks correct. You go to 2 states and then you go to 1. Oh. Yeah. 2 states. So why does it say 2 states? Maybe you don't end up with 2 states. You end up with 1. But as far as I understand, you end up with only 1. No matter which path you follow. Okay, well, anyway. It's not an issue with what I've done. It's just, like 2 states means there's 2 individual states. So they're expecting the answer to be that number there. How does this compute it again? Sum all these hashes. Oh. But then, if there's only 1 state at the end, it should look like this. 161, 222, 161. Total of 2 end states. They're saying there should be 2 end states. All right, let's just have a look at what this looks like. So I can't think in 3D, in 2D. We start with 0, 6, 0, 2, 2, 2, 1, 6, 1. Now, I don't see any captures. Yeah, we can't capture. So, one move is to put a 1 there. Or, we can put a 1 there. And in either case, the only other thing we can do is put a 1 in the other slot. So, those are not... Oh, wait. Oh, they don't want us to they want us to, so that those two end states are identical, but they don't want us to count them as one state. They want us to count them separately. Oh. So basically, there's 2 end states, but they're both identical, and they're both this. And now if we sum them, you get 2, carry the 1, 3, so that would be 3. Yeah, that's what they're doing. Oh. Damn it. Okay, fine. That means... we can't... We don't use sets here. We use lists. No, lists would be inefficient. We actually want to use a counter. So basically count, or given state, have a counter for how many times that state is, in theory, being stored. In this case, it should be a counter saying this state is stored 2 times. If we try and store it individually, separately, it's going to use too much. So, okay, we want to import a counter. Okay, so these are counters now. Alright, DJ. See you next time. This will probably be the only stream I do of this. I'm not that interested to further optimize it, so yeah, we'll see how quickly I can get to a final answer here. So now we have to say this. Now we make a fresh counter. So we want to say for state count in non-file of states dot values dot items even. That gets the count as well. So for next state, in get next states, blah blah blah. If it's a final state, then final states. We add that count, we move that count across. Otherwise, we do new states. Let's see what that looks like now. So we should get the states stored separately. Finals 161, 222, 161, 2. That's what we want. Okay, good. All right, now we want to compute the hash. So let's just say hash. No, you're not allowed to use that word. Final hash equals 0. And then we say for state count in non-final states dot items. So so we get the digits as a list. So it's going to be like dot join string for the in or just say we map string to date.get digits, join them up, and then turn that to an int. That is the hash of that state. So we do final hash equals final hash plus, and we multiply it by count. And then that whole thing we do modulo and noise. Modulo 2 to the 30. And then I guess we can just duplicate this for final states as well. I mean, we could concatenate. Well, that'll probably create another object. I don't know. This is efficient. Do it like this. Count in final items, and then print final hash. So it's an integer, right? Correct. Correct. All right, try all the test cases. We need to stop logging stuff now, because it's probably computing. Also, I don't think we can manage for these test cases. I'm not using an efficient algorithm here. Timeout, yeah. Well, that's cool. Interesting. So what could I do to actually... Oops. Do we even need caching here? We tried turning the caching off. Like, oh, it works now. Okay, caching was harming us. And I think I was half expecting that because... I don't think we're doing that many duplicate get next states of states. I think after each layer of depth, it's not common to then have states you had earlier, because as you add dice to the board, in general, the board is getting filled up, the numbers are getting bigger, you're not really revisiting old states that often, so I think we don't actually really want to do that. How far can we go now? Oh, oh. Okay, so no caching. Just have their servers crash to my sure it still works for these as well. We're managing. I don't think we're gonna manage all the test cases though. Alright, if we're not using this, then we shouldn't actually be using this method at all. We should... say... take that out. And we should actually be saying state.getNextStates. What? We failed that one, but we didn't pass that. We passed that one, but we failed this one. Try this one again and see what was it a timeout. So we passed all of them except for this one. Damn it. I mean, we could submit this. We'll still get a... Yeah, we ran out of time. Depth was 20. Now we need to think about to improve this. I think some of these methods, like for example, get neighbors, we don't actually have to have these for loops. We can just straight up hard-code a dictionary which says for each cell what the neighbors are. That might actually be better. We can like just hard-code that. That might save us some time. Get next states. Get next states I think is fine as is. Like it's not a very trivial thing to do, so I don't really see a way to change this much. Subset. Yeah. I mean subset power set is efficient really. It's not, and it's only going as high as 4 elements. And we've used a counter. I don't see like we... That seems to be... Yeah. And this bit's fine because it's just a sum. Like if we built those counters up in the first place, then it's not going to use much more computation just to sum them up. So yeah. The biggest time sink is probably this. So it needs a smarter algorithm, I guess. I don't know. Just play them all and see exactly what the result is right now.
not bad, but if we don't get 100%, then that means we are way down in the leaderboard, because a lot of people have got 100%. And then it's a question of how fast they do it. But if we don't get 100%, then that kind of sucks, doesn't it? Yeah, we passed all of them except for this one. Huh. They're submitting. What if we get lucky and... Because they won't have the same test cases. So number 11 won't actually be there, but they might have something just as hard. Alright, just let it compute. Oh dear, so... Uh, 63%. Interesting. So we passed the test case they gave us, but we didn't pass the equivalent actual test case, which we don't have access to. Yeah. Okay. Where does that put us on the leaderboard? I'm not that interested in this competition, to be honest. And we're just going to get completely eclipsed by all these C++ people doing cool stuff with bits. But where are we? Three, 6, 7? Oh, but there's not that many people in the competition, are there? 701, so we're like in the top 50, 60%. Okay, fine. And most of these haven't even submitted, really, so... Well, they haven't even done anything that works, so... Oh, wow. So amongst the people who have actually done something that works, we're pretty much at the bottom. 3, 6, 7. Alright. Yeah, this is where all the cool Python people are. Not really. Well, actually, lots of people did pass it with Python. The question is, do I want to carry on or just call it there? Like, it's not really that fun to continue if we know we're at a huge disadvantage with Python. I mean, I should still try to 100% it, but what we gonna do now? Can we... So the digits, we shouldn't really have this method. It should just be stored along with the state. Also, garbage collection. Like, can we just avoid garbage collection? Let's see if we can... So here, non-final states, new states. Let's just say this is actually a list of counters. And we always take the last one. New states is a new counter. And we take the last one. And then we simply append. So if we do that, then it's actually keeping all the past counters in memory. No garbage collection, no deletion. It'll be a huge bunch of stuff stored, but that'll probably save us some time. Let's try that.
Like, basically keep everything in memory, don't delete anything. We could try submitting this and see if that improves things. Because we're probably spending a lot of time on the garbage collection. If it's doing it. I don't know exactly when it's choosing to do it, but the moment we replace one variable with another, then the old variable is a floating thing. We just get rid of it at some point. Still fails on that. Let's just try submitting it and see what happens. Do I think this bit is sufficient? Yeah, because it's only doing it a number of times. That's not a big deal. Some of these methods, like get digits, I think instead we should just store the digits as a list or tuple or whatever here. So it should just be like this, digits. As like we don't want it to be a list. We don't want it to be modified though. Actually, I think what we're doing is not actually that bad. Because when we request the digits, we do actually want a fresh list. We don't want to return a list that could be modified in place. Five 55826. We did better before. Huh. And that could be stored. Suppose final state should be so like is final state is a bool, and then we say we do is final state be basically 0 not in that. So whenever we requested this, it's not a method, we just do that. Else. So we'll leave digits alone. Alright, neighbors is a weird one. I don't like doing this every time, but we can see if that improved anything. These are little things though. I don't know. maybe this... Maybe hard coding all the permutations instead of calling combinations. I don't know. Let's submit. I think I'm done. I'm not interested to actually try to optimize this. It's not the fun side of algorithms for me. This is the boring side. Admittedly, though, there is some good algorithm work to be done. Like, I don't think this algorithm is actually the best one. There's probably a much better way of doing get next states that will eliminate a lot of this stuff and be more smart with how we're doing it. I just can't be bothered. Let's just see what we get. I was really hoping for a... Oh wow, we're just getting slower and slower each time. Oh, we failed that one now. Really? Is it just... Is it a little bit random? Like, even using a class at all, like, we don't really need to. Like, just storing it as a tuple of integers, or even as a 32-bit integer, and then doing the logic on that integer in place is probably a lot more efficient. Yeah, that's it. I don't really want to continue. So our best score was 62%, our first submission. Let's go with that. We'll hope for a proper bot programming competition. Yeah, this is not... This is really not much different to any of those optimization puzzles that are regularly added to the site anyway. Like, I don't... This doesn't seem like a special event to me. This is just a normal... Like, there's a whole... They got loads of these puzzles. This is no different to any of these, really. Well... Like these, basically. Okay, there's not actually that many of them that are categorized as optimization. But, I mean, if you look at some of these past ones, they actually had animations and everything, so... If you're not going to include that, which is part of the fun, then this doesn't feel much more than some of these basic ones, like this, for example. Oh wow, even this has an animation, see? Alright. Okay, yeah, I was a bit disappointed to see that's all this was. Is anyone else doing it that I can raid? I searched on YouTube, no one has been streaming this much. But then again, it was only released the other day, so... Alright. That's it then. So, we'll expect the next proper bot tournament might be in the fall. It feels like they've been cutting down on them. I guess they're expensive to run, I don't know. When was the last? The last one was winter, and then before that was the fall. Was fall also the bot challenge? Yeah, it was. Yeah. Alright. Well, let's just hope for something maybe in the summer or the fall. No one else is doing coding games, so I'm not going to raid. So, see you next fall, I guess. Bye-bye. And in the meantime, I'll probably do Advent of Code in the summer. Advent of Code 2020. 20 or 19, 18. I think 18.